Hello, welcome to my talk on why we need dimensional analysis. This is the part 2 of the topic. In this talk, I will tell the detailed difficulties in direct fluid dynamics. In this talk, I will use an example of a simple flow in a horizontal pipe, and then give a discussion on the general physical relation between the flow friction and the relevant parameters in a direct expression. And then I will talk about the difficulties on how we can obtain the desired data and the difficulties in representing the data, how we can find the relation between the fluid friction and the relevant parameters. And finally, I will give an example how Reynolds carried out the dimensional analysis for his experiment. The example we use in this talk is the flow in a smooth horizontal pipe with a diameter d and the flow velocity v, and we suppose the fluid density is rho and the viscosity mu. The target is to study how the fluid friction will change in terms of these environment parameters: v, the velocity of the flow; d, the diameter of the pipe; rho, and mu. That means when we change each of the environment parameters, how the fluid friction would change. It was well recognized as early as in 1880s. See the Reynolds experiment. The flow in the pipe could have two different forms: the nominal flow, when the flow velocity is very low, and the turbulent flow, when the flow velocity is high. This velocity profile is the average velocity in turbulent flow. In fact, the turbulent flow profile should be something like this, and it is depending on time. And it was also found that the fluid resistance in a tube could be either proportional to the square of the velocity in the turbulent flow, or proportional to the velocity in the nominal flow. And the question would be, in what dependencies of the environment parameters v, d, rho, mu, the fluid resistance in a tube would be proportional to the square of the velocity or proportional to the velocity. We will see whether this would be purely dependent on the individual parameters or depending on certain combinations of these parameters. In here, we would like to make an analysis based on the physics and from the experience. So the fluid friction would be dependent on the following parameters. Here, the pipe is assumed as smooth, so for simplifying the problem, the fluid friction would be dependent on the fluid velocity v. This is for sure, since a larger fluid velocity might cause a larger fluid friction. Pipe diameter is again can be understandable. For a large pipe, the fluid friction would be larger. The fluid viscosity, it can be understandable. For a larger fluid viscosity, the fluid friction would be larger. Fluid density might be important for the fluid friction, and we will see how important this would be in the actual analysis. So for a general expression, the fluid friction can be expressed as this: if R, the fluid friction, is the function of 4 physical parameters or the environment parameters, V, the fluid velocity, d, the diameter of the pipe, mu, the fluid viscosity, rho, the fluid density. Or we can write the function as f1 of the 5 physical parameters: the fluid fraction, velocity, diameter of the pipe, fluid viscosity, fluid density is 0. And both of these functions can be used in the dimensional analysis. Here we use the first expression in this talk. If we look at the problem for the fluid fraction in a direct way, we may have the difficulties in obtaining the data. For instance, if we use the numeric method to solve the fluid dynamic equation to obtain the dependencies of the fluid fraction on the fluid velocity, the pipe diameter, fluid viscosity, fluid density. Generally, we need to change 3 or more times for each of the parameters v, d, mu, rho. And these parameters should be covered the parameters of inches, and 3 is the least number for the changes of each parameter. So for this simple problem, the total combinations of changes would be equal or larger than 3 times 3 times 3 times 3 because of the 4 physical parameters. That means we will have more than 81 combinations for this simple problem. Imagine if we solve Navier-Stokes equation for all these individual cases, more than 81 cases, it would be very time-consuming. And if we use the experiment method to study the problem, in a similar way, we need to carry out the experiment with the changes for each of the physical parameters, and each parameter should be changed more than 3 times. If we change the velocity of the flow, it is easy because we can easily change the flow rate of the flow in the pipe. So this can be easily done. If we need to change the diameter of the pipe, it would be difficult because we need different model. So in the experiment study, we need 3 or more different models for testing. And changing the fluid viscosity, this can be hard if we are using different fluids. However, as Reynolds has done, we can change the temperature of the fluid, which would change the fluid viscosity very much. And if we need to change the fluid density, this can be difficult if we change the fluid. And also, if we need to change the fluid for the experiment, the fluid viscosity and density would be changed together, not individually. So we can see the problem in the experiment. Here we are not mentioning how many combinations of the experiment we need to carry out, same as this more than 81 scenarios for testing. Suppose we manage to get the data as we use the numeric simulations or experiment studies. The next difficulty would be the data presentation, how we can build the relation between the fluid friction and all these parameters. Here, suppose we have all the required data, and then we look at the dependence of the fluid friction and the velocity. So here we can see for diameter d1, so we have the curve like this. The fluid friction is the function of the fluid velocity given as this. However, we need to change the diameter for looking at how the pipe diameter would have influence on the fluid friction. So we see 3 different diameters in the test. And we see here the plot is only for the relation of the fluid friction depending on the fluid velocity and the pipe diameter. And we assume the fluid viscosity and density are same. Now in here, we need to include the fluid viscosity in the analysis. So for the third parameter, the fluid viscosity, we need to look at least 3 different values, mu1, mu2, and mu3. And then we should have drawing like this for different fluid viscosities. Obviously, the plot is much more complicated if we include one more parameters, the fluid viscosity in the analysis. However, for this problem, we may also need to look at the changes in the fluid density and see how the fluid density would have the influence on the fluid friction. So here we include the fourth parameter, the fluid density. And then we can see for density rho 1, we have a drawing of the fluid friction with the fluid velocity, the pipe diameter, and the fluid viscosity. And to change the fluid density, we have different plot. And for the third density, we have another plot. So we can see if we look at the friction dependencies on these parameters, we would have the plot like this, very complicated. So how we can see clearly the fluid friction dependencies on all these parameters? It is very difficult and very complicated. Now a question would be, can we find a way to simplify the problem? The answer for this question is yes, and the powerful tool is dimensional analysis. Osborne-Reynolds may be the first one who systematically carried out the experiment and the analysis to explore the flows from laminar to turbulent transition in horizontal pipes. He managed to obtain a non-dimensional number. Now it is named as Reynolds number. He did this without the knowledge and the theory of dimensional analysis, since the theory was established after his work. Today, Reynolds number is the most important and the most used non-dimensional number in fluid dynamics. And we can see it everywhere in fluid dynamics, in laminar flow and in turbulent flow alike. The drawing shows Osborne-Reynolds studied the flow transition from laminar to turbulent in the circular pipes in 1880. In his experiment, he examined the important issues, such as in what circumstance the fluid resistance in a tube was proportional to the square of the velocity or proportional to the velocity. And did the laminar static motion hold up to a critical value, and then eddies can be in as the turbulent flows. For instance, the eddies can be in at a certain value of the combinations of the parameters given at this. Here, rho is the density of the fluid, c is the radius of the pipe, v is the flow velocity, mu is the fluid viscosity. Reynolds carried out the experiment using 3 different pipes of different diameter, and he changes the temperature of the fluid for different viscosity of the fluid. And he tests for different fluid velocities. This can be found in the publication in the reference. In the analysis of the experiment data, he analyzes the many different combinations of the parameters, and he found and decided that his K number is a very good non-dimensional parameter for indicating the fluid state. K number is defined as this: rho dV divided by mu. So D is the pipe diameter, V is the mean velocity of the flow in the pipe, rho is the fluid density, mu is the fluid viscosity. And now the K number is named as the famous Reynolds number, as we are using today. In 1895, Reynolds published the result of his non-dimensional K number. For laminar flow, K should be smaller than 1900. See this laminar flow. And the turbulent flow, when K is larger than 2000, see the turbulent flow this and here. And in between, the flow is in transition. Today, the accepted critical Reynolds number RE would be slightly different from the Reynolds result. It is well accepted the Reynolds number for paper flow, the laminar flow would be smaller than 2300, and for turbulent flow, Reynolds number should be larger than 4000. So we can see these are different from the Reynolds result. It is probably because the more accurate measurement. And also we can see this even for turbulent flow, Reynolds number for larger than 4000. And if we look at the pipe of a diameter 0.5 meter for water, and we will see how big of the flow velocity such that the Reynolds number would achieve the Reynolds number for turbulent flow, RE equaling to 4000. The answer for this would be given as we calculated as this, and we use the water viscosity and the Reynolds number and the density of the water, diameter of the pipe. So the velocity would be 0.04 meters per second. So this is a very small velocity. That means in most cases, the flow in the pipe would be turbulent. This is why if we see the difference of the kinetic Reynolds number from the Reynolds result, it doesn't matter too much because this hardly happened in the practical flows.